Okay, hello. Um, in this lecture, we're going to talk about calculating type 2 error. So far, we've been focused on alpha and type 1 error. Um, this will sort of complete the picture when we discuss type 2 error, and this will involve also talking about the sample size again. So first, before we start, just a comment about the way the test is specified. So until now, we've been specifying the tests like this. So our test for the tires, for example, so our tests have been, the composite has been of the conditions has been the whole set. So we had something like this. The null hypothesis was H0 greater than 20,000 and HA, the expected value, is less than 20,000. This was with the tires, right? And the company boasted that the average life of a tire was 20,000 miles. And we wanted to find significant significant data that gave evidence to the contrary of that. So this is the way we pose the hypotheses. Now, one thing you notice the book can do, and the book does, is they just use the equality here. They don't count. You notice we're always taking, when we calculate type 1 error, we were always taking the boundary point here at 20,000 to be the condition that was true, because that would make the probability of type 1 error the highest. Type 1 error, you remember, is choosing HA when H0 is true. So if mu is equal to 20,000, that's very close to some of the mu's in here, and you would get the highest probability of making a type 2 error. When mu is bigger than 20,000, it's not as likely, so we didn't consider that. We just bound the type 1 error. Well, another way to do this, and this is the way the book actually introduces it, is they make the null hypothesis just mu equals 20,000. Really, you're trying to reject or not reject that condition, so it's fine to just use the boundary alone. So alternately, and this is the way the book usually does it, but other books do it this way. Alternately, we could do the same problem, could make same test. It's the exact same test, really. Depends how you want to. By H0 mu equals 20,000 and HA mu still less than 20,000. Because the idea is now I would like to, just as up here, I'm trying to reject this and show this. So I can reject that mu is 20,000. It's really essentially what I was doing here, because I was taking the boundary here anyway. So these are the same test, really. Okay, let's try to point that out more as we go forward. Okay, so then with the definition of alpha, then alpha is equal to the probability of type 1 error, right, in this test, which is just the probability that we choose HA, test stat, so choose HA, test chooses HA, given mu equals 20,000. Okay, and this is probability of type 1 error. While beta is the probability we choose H0 given HA is true. Well, usually HA is not a single mu equal to a single value, or P equal to a single value. It's a set of values. So here it's not really clear. If I can't really set mu equal to the boundary here because that would be setting it equal to 20,000, then I'm already in H0. I have to set it something in HA and show that H0 is true, or show that the test chooses H0. Beta, the probability of type 2 errors have to be specified depending on what you select as mu. So the idea is you pick something for mu that you might think you really want to claim this condition's true. You really want to claim, like, for example, if mu is really, say, I don't know what you would consider important, you want it close to 20,000 but less, say 19,000. Say when mu is actually 19,000, you really want to claim this, so you want to examine the probability of an error when mu is 19,000, and so then you would define it that way. So for beta, we'll go beta and we'll put mu down here, something like this. We'll write it mu A to mean that it's in the alternate hypothesis set. So beta mu A is equal to the probability we choose H0. In other words, don't choose HA given, so maybe better, given that mu equals mu A, and mu A is in the set, mu A is in, say, HA. Okay, that's set. Okay, if that's clear. Okay, mu equals mu A, yeah. All right, so this is probability of type 2 error. When mu equals mu A. Okay, so that's the that's how we need to define type 2 error. All right, so let's do an example to see what shakes out of this. So I think we can redo the example. I hope I don't need the computer, but yeah, so suppose we have, so for example, we have something like tires, right? Like N equals 60. Y bar was 19,250 and S 1,000. And suppose we want to test this test H0. So this is the company claiming the lifespan is 20,000, but we just sampled 60 and found the average was 19.25. And we want to make a test to see if this has evidence that the claim is false. So H0, let's just use the new notation. Now we'll have mu, which is just E of yi. We'll just have this equal to 20,000. I want to be able to go back between the two notations. And HA will be mu, less than 20,000. Okay, we already found, so our test stat is test stat, and the rejection region we found in a previous lecture was equal to y bar less than 19,788 for an alpha equals 0.05 level test. Yeah. Okay, let's compute. So say find, suppose we really want to reject this at 19.8. So find beta mu equals 19,800. Okay, well, this is just equal to, so we have beta. So let's call this beta. Beta is equal to probability. We don't reject the null hypothesis, so probability that y bar is greater than or equal to 19,788 given mu equals 19,888. Okay. All right, so now this is called large sample testing because we're going to use the central limit theorem. So at this point, I'm going to assume y bar is normal, and I'll make a transformation here. So we have this is equal to, so CLT, and transform to z, just to save steps, z, okay, which is normal, standard normal, is greater than or equal to, I have this minus, so I have 19,788 minus 19,800, so what's that, minus 22? Minus 22 divided by 1,000 sigma over the square root of n, so I can put that up here, square root of 60. Okay, so beta is this, and this is actually a number here now, and I did this, and I get approximately 0.567. So very high probability. I will not reject when mu is 19,800. Okay, even though it's less than 20,000, I probably will not reject. I will not reject it here. So with that probability, so more than half. Okay. All right. I'd like to do another example on this, but that's going to be the next video. So please, sorry, this is off. That will be the next one. Okay.